discovered cutting-edge bridge construction technology and impressive marine transport operations shaping the future of global infrastructure. The Honam high-speed railway, one of South Korea's major infrastructure projects, demonstrates the nation's advanced bridge construction technology through the use of the precast segmental method. This technique, applied in the construction of the Mangyong River Bridge within Section 3-3 of the project, represents a highly efficient and precise approach to building railway viaducts for high-speed trains. The system is characterized by the factory production of pre-stressed concrete box girders, each 25 meters long, which are then transported and installed at the site using specialized lifting and launching equipment. The PSM technique ensures the highest possible construction quality through complete industrialization and mechanization of the process. In traditional bridge construction, concrete casting and curing are performed on-site, which exposes the structure to environmental variables such as humidity, temperature, and uneven curing conditions. In contrast, the PSM approach allows each box girder to be fabricated in a controlled factory environment where temperature, vibration, and concrete mix proportions are strictly monitored. This not only enhances structural strength and dimensional accuracy, but also reduces potential human error and material waste. Each 25-meter box girder is a hollow rectangular beam designed to support both the track structure and the dynamic loads of high-speed trains. After production, the girders are carefully inspected and stored until the site is ready for installation. Transportation to the construction site is carried out using special multi-axle trailers capable of carrying heavy loads over long distances without deformation. Once at the site, large-scale cranes or launching gantries are used to lift the girders and position them precisely on the piers. The installation sequence is carefully planned to ensure both safety and efficiency. Before the girders are placed, the bridge piers are constructed and aligned with millimeter-level accuracy. Temporary supports or bearings are installed on top of the piers to receive the box girders. Once the girders are set, they are adjusted to achieve the designed alignment and level. Afterward, adjacent girders are connected using post-tensioning cables, which compress the segments together, allowing them to behave as a single continuous structure. This technique minimizes the formation of cracks and increases the bridge's ability to withstand dynamic forces during train operation. One of the main advantages of the PSM method is the significant reduction in construction time. Since the production of girders in the factory can proceed simultaneously with foundation and pier work at the site, the overall schedule is greatly shortened. In addition, the on-site assembly process is faster and less dependent on weather conditions. The high degree of prefabrication also improves work safety. as less manual labor and formwork installation are required on elevated structures. From an engineering perspective, the PSM system provides outstanding precision and quality assurance. The use of advanced equipment such as automatic concrete mixers, curing chambers, and precision molds guarantees consistent dimensions and surface finish for each segment. Furthermore, the controlled pretensioning process enhances the durability of the structure, reducing long-term maintenance needs. The mechanized erection process using gantry cranes and synchronized lifting systems ensures accurate placement without the need for extensive scaffolding or falsework, making it ideal for long-span viaducts crossing rivers in urban areas. Environmental benefits are also achieved through this method. Since most operations are concentrated in the factory, noise, dust, and waste generation at the construction site are minimized. The reduced on-site concrete pouring helps protect nearby waterways and ecosystems. NTHE success of the Mangyang River Bridge construction under the Honam high-speed railway project highlights the advantages of adopting industrialized bridge construction technologies. By combining precision engineering, advanced materials, and automated processes, the PSM method delivers structures that are not only strong and durable, but also aesthetically refined and environmentally friendly. The project involved the transport of two massive ship unloader machines from Stettin to Eemshaven, organized and executed by Trend Project. Each unloader, weighing approximately 900 tons, required complex logistics planning and specialized heavy lift operations. The loading operations took place in Stettin in December 2012, where the units were carefully positioned and secured on board the WB9 barge. Trend Project was fully responsible for all critical stages, including loading supervision, lashing, sea voyage calculations, and discharging planning bought head. During transport, precise stability and motion analyses were conducted to ensure the safety of both cargo and vessel in challenging sea conditions. The massive unloaders were meticulously fastened, using heavy-duty steel lashings and supports to prevent any movement during the voyage. After successful sea transportation, the discharging process took place at the port of Eemshaven in January 2013. Unloading such large structures required synchronized teamwork, hydraulic lifting systems, and the use of self-propelled modular transporters, SPMTs, for final positioning on shore. The entire operation demonstrated Trend Project's expertise in heavy cargo logistics, combining engineering precision with maritime experience. This project stands as an example of successful coordination between design, transport, and on-site handling of oversized industrial equipment. The Lowestoft Gull-Wing Bridge is a remarkable Bascule bridge spanning Lake Lothing in Lowestoft, Suffolk, England. Designed to ease congestion and improve connectivity between the north and south of the town, it stands as one of the most significant infrastructure projects in the region. Construction began in March 2021 and continued for over 3 years, culminating in the bridge's opening to traffic on September 7, 2024. The official inauguration followed on November 19, 2024, conducted by Princess Anne. The arrival of the bridge's major steel components marked key milestones in its construction. On March 29, 2023, two enormous steel sections weighing more than 400 tons in total were transported by barge from the Netherlands to Lowestoft. These sections formed crucial parts of the Bascule mechanism and central span. A few weeks later, on or around April 24, 2023, Sections 1 and 3 of the South Approach Viaduct were delivered by barge and carefully positioned at the construction site. Hello Radio and local media documented these events, capturing the impressive engineering and logistical effort involved in transporting and installing the components. The scene during the arrival of the SAV spans on May 3, 2023, was particularly striking. Massive steel sections were maneuvered with precision by cranes and barges in the harbor, while workers and engineers coordinated each step to ensure perfect alignment. The calm waters of Lake Lothing reflected the towering bridge structure as it gradually took shape. Now fully operational, the Gullwing Bridge not only enhances transport efficiency, but also stands as a new landmark of Lowestoft, symbolizing modern engineering achievement and regional development. The skidding operation involved loading a massive 875-ton offshore module, designated Kvarner B02 for ConocoPhillips, onto the UR96 pontoon. The operation was carried out by Energomontage Polnoc Gdynia, a company specialized in heavy offshore structures. Using hydraulic skidding systems, the module was carefully shifted along steel tracks from the assembly area onto the pontoon deck. Precise synchronization of jacks and control systems ensured balanced movement and structural stability throughout the process. The entire procedure followed strict Norwegian offshore guidelines, ensuring safety, accuracy, and compliance with international standards. Documentation and lead-out were meticulously prepared and supervised by qualified engineers. The successful completion of the skidding marked a key stage in the module's preparation for transport and offshore installation. At Han Gai Port in northern Vietnam, cargo unloading operations are efficiently carried out using the Liebherr CBG 360 floating cranes. These high-performance cranes are specially designed for bulk handling operations at sea and nearshore terminals such as On Net, Cam Pha, and On Mia. Each CBG 360 crane features an impressive lifting capacity of 45 tons at a maximum outreach of 36 meters, enabling it to handle a wide range of materials from coal and clinker to fertilizers and minerals. The cranes are equipped with 4 rope grab buckets with a capacity ranging from 23 to 35 cubic meters, depending on the type and density of cargo being handled. This design ensures optimal stability and precision during each lifting cycle, even under challenging marine conditions. Operating from a floating platform, the cranes transfer cargo directly from ocean-going vessels to barges or to the port's conveyor systems. Thanks to their operational capacity of up to 800 tons per hour, the CBG 360 cranes provide a reliable and efficient solution for continuous bulk unloading. The hydraulic and control systems are optimized for smooth, energy-efficient performance, while Liebherr's robust design ensures durability and safety throughout prolonged operations. During unloading at Honam port, the floating cranes are precisely maneuvered alongside anchored ships. The operators then lower the grab into the ship's hold to collect the bulk material and discharge it into waiting barges positioned nearby. This floating crane system significantly reduces the need for shore-based infrastructure, offering flexibility and high throughput for large-scale maritime logistics. With their advanced design and exceptional efficiency, the Liebherr CBG 360 floating cranes play a crucial role in maintaining the productivity of Honam port and supporting the continuous export and import activities vital to Vietnam's maritime trade network. The SpaceX drone ship returned to Port Canaveral on Monday, November 19, 2018, carrying the Falcon 9 first stage that had successfully launched the SHALE-2 satellite into geostationary transfer orbit. On the first day, the booster's arrival was observed without much further activity. The next day, SpaceX engineers lifted the booster from the drone ship and placed it securely on a stand for inspection and processing. On the third day, the recovered stage was lowered to a horizontal position and loaded onto a transporter for further transport to SpaceX facilities. This careful recovery and handling process highlights SpaceX's commitment to reusability and efficiency in modern spaceflight operations. The process of pouring a concrete slab using the precast panel LB deck method, which enables fast and efficient construction. The precast panel system allows repetitive and simplified work with fewer on-site operations, reducing construction time and minimizing the risk of accidents. Since no formwork removal is needed, subsequent slab work can proceed immediately, helping prevent falling materials and worker injuries. After the precast panels are installed, reinforcement bars and drainage inlets are placed. Before pouring, a meeting is held to identify and solve potential issues. During concrete placement, internal vibrators are used vertically at regular intervals to compact the mix. The vibrator should penetrate slightly into the lower layer and remain until cement paste appears on the surface. It must be withdrawn slowly without lateral movement, and at least 2 vibrators should be prepared in case of failure. Finally, curing is done by applying a curing compound and covering the surface with wet fabric for moisture retention. The construction of modern concrete bridges often employs the Precast segmental method, PSM, a highly efficient and precise technique designed to shorten construction time, enhance quality control, and minimize on-site work. This method involves manufacturing pre-stressed box girder segments in a controlled factory environment, then transporting and assembling them at the bridge site using specialized erection equipment. The process combines advanced engineering with systematic field operations, resulting in durable and elegant bridge structures suitable for highways and railways. The PSM technique begins with the production of precast box girder segments. Each segment, typically 25 meters long, is cast in a dedicated precasting yard using high-strength reinforced concrete. The segments are formed inside steel molds that ensure accurate geometry and smooth surface finishes. After concrete curing and pre-stressing, the segments are demolded and stored for quality inspection. This controlled production environment helps achieve consistent strength, precise dimensions, and superior durability compared to cast-in-place methods. Once the precast segments are completed, they are transported to the bridge erection site using heavy trailers or special transporters. The delivery schedule is carefully synchronized with the erection sequence to minimize storage at the site. Each segment is marked with an identification code corresponding to its exact position in the bridge span, ensuring that assembly proceeds in the correct order. At the bridge site, the launching girder or bridge erection machine is installed. This massive steel truss structure, which spans between two bridge piers, serves as a movable assembly platform for lifting and positioning the precast segments. The launching girder can move forward along the bridge alignment, allowing continuous construction of span after span without the need for scaffolding or falsework below. This feature makes it particularly suitable for bridges over rivers, highways, or difficult terrain where ground access is limited. The segment erection process starts by positioning the launching girder over the first span. The first precast segment, usually located near the pier, is lifted by the machine's winch or hydraulic lifting system and placed precisely onto temporary supports. Subsequent segments are hoisted one by one and aligned with millimeter-level accuracy using hydraulic jacks and alignment sensors. The segments are connected through high-strength epoxy adhesive applied to their matching surfaces, which ensures watertight joints and uniform load transfer. After alignment, post-tensioning tendons are threaded through ducts running across the entire span. These tendons are then tensioned using hydraulic jacks, compressing the segments together to form a single continuous girder capable of supporting its own weight and live loads. The post-tensioning process is critical, as it provides the necessary structural integrity and eliminates tensile stresses in the concrete under service conditions. Once a span is completed and fully stressed, the launching girder is advanced to the next span. This operation, known as self-launching, involves sliding or rolling the massive truss forward along temporary rails placed on the newly completed deck. The process is repeated systematically, allowing rapid progress along the bridge alignment. Each new span is connected to the previous one, and continuity post-tensioning is applied to ensure a seamless and robust structure. During the entire operation, safety and precision are paramount. Engineers continuously monitor alignment, stress levels, and joint conditions. The use of advanced sensors and computer-controlled systems in modern launching girders enhances both accuracy and safety. Environmental impacts are minimized since no scaffolding or large falsework structures are required, and the work area below the bridge remains largely unobstructed. Finally, when all spans are in place, the bridge deck is completed with surface finishing, waterproofing, and the installation of expansion joints, parapets, and safety barriers. Asphalt or concrete pavement is laid on top, and the final inspections are carried out to verify alignment, strength, and deflection criteria. In conclusion, the precast segmental method combined with a bridge erection machine represents a modern, efficient, and sustainable approach to bridge construction. It allows for high-quality fabrication of components, rapid on-site assembly, and minimal disruption to existing infrastructure or the environment. This method has become a preferred solution for long-span concrete bridges worldwide, demonstrating the power of precision engineering and innovative construction technology in shaping the future of transportation infrastructure. The Taiwan high-speed rail bridges were constructed using the full-span launching method. In this method, each precast box girder, weighing around 800 tons, was manufactured at a casting yard to ensure high precision and quality. The completed girders were then transported to the site using special self-propelled modular transporters. A large launching gantry was employed to lift and position each full-span girder directly onto the piers. This method significantly reduced on-site construction time, minimized traffic disruptions, and improved safety and alignment accuracy, making it highly suitable for large-scale high-speed rail bridge projects. The construction of a Super T-beam bridge involves the precise coordination of heavy lifting and placement operations. One of the most critical phases in this process is the transportation and installation of the precast Super T girders. These beams, typically made of high-strength reinforced concrete, are large structural members that form the main support of the bridge deck. Their size and weight, often reaching several tens of tons, require specialized handling equipment and careful planning to ensure both safety and accuracy during installation. First, each Super T beam is transported from the precast yard to the construction site using a multi-axle low-bed trailer. The trailer is designed to evenly distribute the beam's load, minimizing stress and vibration during movement. Escorts and traffic management teams coordinate the transportation, ensuring a clear route and maintaining the beam's stability throughout the journey. When the beam arrives at the site, it is positioned parallel to the bridge alignment, ready for lifting operations. In Skidding. For installation, two large crawler or mobile cranes are deployed, one positioned at each end of the beam. Before lifting, both cranes are securely stabilized on firm, level ground with their outriggers fully extended and load charts verified. Rigging crews attach heavy-duty slings and lifting hooks at the designated lifting points of the beam to ensure a balanced and safe lift. The lifting process requires close synchronization between the two crane operators. At the supervisor's command, both cranes lift the beam simultaneously and slowly to prevent twisting or uneven loading. Once the beam is clear of the ground, it is carefully swung and aligned over the bridge piers or abutments. Communication between the operators, riggers, and signalmen is continuous throughout this stage to maintain perfect coordination and avoid sudden movements. As the beam is lowered into place, site engineers ensure that the bearings or neoprene pads are correctly positioned to receive it. The beam is then gently set onto its supports, and temporary restraints or clamps are applied to secure it until the next beams are installed. This procedure is repeated for each subsequent Super T beam, with precise spacing maintained according to design specifications. Finally, once all the beams are in place, bracing and diaphragms are installed to stabilize the structure before the bridge deck is cast. The dual crane lifting method provides excellent control and flexibility, allowing for accurate placement of large beams even in constrained working conditions. This technique ensures structural integrity, minimizes risk, and enhances the efficiency of modern bridge construction using Super T beams N.